So size exclusion chromatography is, as the name suggests, a size-based separation. So size exclusion chromatography, we are going to abbreviate SEC, just like the Southeast Conference, I guess, if you're into that kind of thing. I'm a Florida State guy, so I'm into the ACC, but whatever. Size exclusion chromatography is a size-based separation. And what we see in these chromatograms is something that looks like this. I think this is the very last thing I drew on the board before we left and the world imploded. We see these peaks. Okay, and we said that basically the smaller stuff has a higher retention factor. And the larger stuff, larger particles, have a lower retention factor. And we said there's these two special peaks, right? I'm going to call this 1. I'm going to call this 2. So what are these? Well, peak number 1 is called the total exclusion peak. And what's happening in the total exclusion peak, these are all molecules or particles or materials that went through the column, all analytes that were too large to partition into the stationary phase. We'll take another look at partitioning in the stationary phase in just a second. We'll draw out the figure that we drew out last time. But real briefly here, we'll point out that this means that there's no size-based resolution, RS, above some critical size, right? So everything that's too big, whether it's very, very, very much too big or whether it's just a little too big, everything that's too big is going to get clumped into that one peak. Okay, the second one here, 2, this is called the total inclusion peak. Total inclusion peak, forgive my hand there we go. And this is basically all analytes. Small enough to partition into all stationary phase pores. Hope you guys can see my handwriting here. I'm going to do a little bit better as this online semester goes on. Okay, so everything that's small enough to partition into all the stationary phase pores. So let's remind ourselves of the picture of what this partitioning process looks like. And this we drew on the board. This might already be in your notes because we drew this on the board before we left. But of course, we were all fearing Armageddon, so maybe we forgot to get it in our notes, or maybe we burned our notes to stay warm. I have no idea. Something crazy is going on out there, guys. But the concept is this. You have a stationary phase particle. We're going to draw just one of them. There's a stationary phase particle. And these things are not solid sphere. They're not usually solid spheres like I've drawn this. They're usually porous, right? So they have these pores. I'll draw them like crags going deep into the depths of this particle. And you can see that these pores have various different sizes, right? Some of them have big openings. Some of them have relatively smaller openings. There are these narrow constrictions that can be present in the middle there that prevent things from getting past. And so if we have a range of sizes of particle or analyte, there we go. And these things can diffuse in solution past this particle, while these small things are going to have no trouble diffusing all the way in here, right? But larger particles, like this one, for example, they may be able to get into part of the pore, but there's going to be some restriction at which their only option is to come back out. Again, all just by diffusion, all just by random walk motion in solution. And still there's going to be other particles that are so large that they can barely, so I think, I don't know, just the way I've drawn this, that's probably large enough to spend a little bit of time like that maybe inside that particle. But this guy for sure, too big, can't get in at all, right? So this thing spends no time in the stationary phase particle, all of its time in the mobile phase particle. Sorry, in the mobile phase, right? Moving in the mobile phase past the stationary phase particles. And so this is this basis of separation where small things spend a lot more time in the stationary phase. When they're in the stationary phase, they are stationary. Surprise, surprise, spoiler alert. But when they're in the mobile phase, they are mobile. And so they are moving faster towards our detector. That means that these things move faster and come out first. They elute first. That's the same thing as saying they have a low retention factor, which is lowercase k, right? Whereas these things, on average, move slower because they spend more time stationary inside the particle. They elute later, exactly as we just described in the chromatogram. And as such, they have, where am I going to write this? Here we go. They have high values of lowercase k. And so the example that we talked about last time, the thing that gives rise to this concept of total inclusion and total exclusion peak is if I take another particle here, a really, really, really big one. It has basically, we're going to say that's a little bit bigger than that. I don't know if it really is. But it basically has the same access to inside this particle that that one did. And that gives it the same value of retention. They will both end up, despite being different sizes, in the total exclusion peak. And we can imagine even smaller particles here that also have full access to every depth of every pore. And so there will be no resolution here either. They will have the same K values and they will end up in the total inclusion peak. So let's think of a mathematical way to discuss, or at least a numeric, a quantitative way to discuss this concept of total inclusion, total exclusion, and resolution in size exclusion chromatography. And it starts with a concept we've used over and over again, but I'm going to remind you of it right now, which is, so our x-axis here is time, and we get peaks, right? Chromatographic peaks. And we are used to thinking about these in terms of their retention time, T sub r. Or if we really care about describing these things in a reproducible way that we can transfer to other labs that describe the extraction and not just the amount of time it took to come out in our lab, we can convert this to a retention factor. But there's another thing we can convert this to, and we've talked about this. If we know the time it takes for something to come out, and we know the volumetric flow rate, so just to be clear, volumetric flow rate implies something in units of volume per unit time. If we know this, and we know how long it takes to come out of here, we can talk about not its retention time, but its retention volume. We've talked about this being a really useful factor, useful way of describing retention in gas chromatography, especially, but it's also very useful here and really can be used in any mode or any method of chromatography. So this is our retention volume. And pretty much all the math that we've done that applies to TR applies to VR. We just need to put our brains into the kind of the volume way of thinking, right? So let's talk about, in terms of retention volume, what these total inclusion and total exclusion things mean. Okay, so first let's start with total exclusion. So if we're saying that a particle is too large to interact with the stationary phase, it is by definition an unretained species, right? And we had this terminology we used to use when we were talking in time about the void time, T0, which we said was always this first little blip of a peak that comes out, right? We'll call that T0. And we called this the void time, so it's directly equal to the void time, which was also referred to as the time for an unretained, that's the key here, unretained species. Okay, we can convert that to volume, and we can call it V sub 0. So if our particles are too large to interact, if our analytes are too large to interact with the pores of our stationary phase particles, then we can assume that their retention volume, so the total exclusion peak, the retention volume for that, V sub r, is equal to our void volume. It is this unretained species. So cool. That's a fairly straightforward description. Our total inclusion peak is something else, right? We're saying that it samples the species in the total inclusion peak has sampled all of the intraparticle volume, all of the porosity of the stationary phase particle. And so in this case, what we can say is that its retention volume, V sub r, well, it certainly sampled the same amount of extra particle volume, the V sub 0, that it takes to get from the head of the column out to the detector, right? All of the extra particle space, but it's also sampled all of the intraparticle volume, which we'll call V sub I. Let's define this over here. V sub I is the intraparticle volume. We've called this before the total porosity of the column. Okay, so we are used to thinking of these things as extractions, right? And it's a little bit difficult for us to think about a partition coefficient here because what we're saying is that there's no enthalpic contribution to extraction, right? So it's difficult to think about it in terms of equilibrium constants. But basically, we can describe the partitioning coefficient in an experiment like this as being the retention volume of the species that we are trying to measure a partition coefficient for minus V sub 0. So this is essentially equivalent to our K factor, right? We can divide that by the intraparticle volume, V sub I. And if we kind of say these are the boundary conditions, right? The total exclusion and the total inclusion, what we end up seeing is that all of our separation happens in a space of this partition coefficient between 0 and 1. So it says between, got a little ahead of myself here, between 0 and 1. In other words, total exclusion peak, K is equal to 0. And for our total, move this up here, see a little better. For our total inclusion peak, K is equal to 1, and all of our resolved space between these two, we have partition coefficients somewhere in that range from 0 to 1. Okay, so let's take a look at the space that we're resolving in here. So we'll call this y-axis To be honest with you, we generally think of this as molecular weight, although the polymer chemists will tell us that molecular weight is not directly a stand-in for size. You can have something that's very heavy and very compact, and you can also have something that's very light, but also diffuse, right? Low density, and so it would have a very large particle size. So the real thing we care about here is size. It's very common to hear this reported as molecular weight, and that's because people are doing this, they're comparing their system that's very well defined, I don't know, some highly branched polymer or some very low degree of branching polymer they're using this technique on. And so they basically are telling you they're normalizing for the size factor. They consider this to be a molecular weight based separation. Okay, so we're going to plot that on the y-axis. We're going to plot retention volume on the x-axis. And what we said is there's some large molecular weight above which we're going to get no resolution. Everything's going to have the same retention volume. It's going to come out as the same peak, right? So it's all of this right here. All these molecular weights come out at the same retention volume. There's some low molecular weight, some low end of this scale where everything samples all of the stationary phase pores. And so they all come out together. They all have the same retention volume despite having different molecular weights. But the space between them, we hope to have a nice linear resolving range between them. And you can essentially select your column materials for essentially better resolving ranges in here. And what that would do is it would squeeze your total inclusion and total exclusion peaks closer together in retention volume, but it would also give you a steeper slope of this resolving range. And that means you'd be able to resolve two peaks that are more similar in molecular weight or size. You'd be able to resolve them a little bit better. But the take-home message here is for this original curve that we just drew, this is the range of retention volumes that correspond to k equals to 0 and k equals 1. Okay, so we get these linear resolving ranges, and they lie between k equals 0 and k equals 1. And they show some range of molecular weights for which we will get effective separation by size exclusion chromatography. But the question that, as an analytical chemist, you're going to need to answer is: I have two sized analytes. Am I going to be able to resolve them on a given column with a given method? And it's a hard question to answer outright, but there are basically two pieces of information that you can use as a rule of thumb to figure out whether or not this is going to work. And so the first thing I want to show you is this website from GE, Health Care Life Sciences. It's basically their product page and sort of introduction to size exclusion chromatography. It's actually a really nice page, and I'm going to try and link to this, if for nothing else than for the animation that they show right here of how size exclusion chromatography works. It's very, very neat, and I will try to make sure you have the link so you can take a look at that. It's basically just an animated version of the particle porosity thing that we drew out a couple minutes ago. But this is a kind of a product listing of their various stationary phase materials. They call it Superdex or Sucrose or Cefacryl. And what it's showing is basically the molecular weight ranges. You can think of these as AMU or Dalton, ranging from 100 AMU all the way up to, 100 million AMU. They're showing the different products' ability to basically have that linear range between what this would be total inclusion to total exclusion for each one of these lines that lines up with one of their products. So that's the first piece of information you need, just to understand what is the resolving range. Actually, if you go to the Wikipedia article, this is the Wikipedia article on size exclusion chromatography. There's actually a table in here that I think is pretty nice, that looks at some really classic, so these Cephedex and Cephalose materials. What these are cross-linked agarose. They're the classic material that size exclusion chromatography is based on. Basically, if you've ever done something like a DNA gel or polyacrylamide gel, if you've ever done any biochemistry kind of work, it's basically those materials, except rather than just a matrix, like a porous matrix, they're actually chemically cross-linked. So it's the same underlying polymer substrate with chains cross-linked to give them nice high stability inside one of these packed chromatography columns. Anyways, the point is these Cephedex and Cephalose materials, and if we go back here, you'll notice these have names like Cephacryl, right? So these are very similar materials. They come in these different flavors or these different model types, and they correspond to different resolving ranges, right? So this is another nice useful table right here, especially since this is not linked specifically to the GE brand of offerings, but kind of the classic Cephedex, Cephalose type materials. Okay, so first piece of information you need if you're going to answer this question, can I resolve my two peaks, is what is the resolving range? And this is the linear range on that chart that we just drew a minute ago. The second piece of information you're going to need is what is the peak capacity? We've talked about peak capacity before. This is essentially the number of baseline resolved peaks that you could possibly include in a chromatogram. And it turns out peak capacity for size exclusion chromatography isn't great. So we've talked about kind of peak capacity approaching on the order of 100 or dozens maybe for classic HPLC, reverse phase HPLC, which we're going to talk about soon. Here, this is a paper from 1982 in Journal of Chromatography A. This is like the top journal of separation science, basically. Looking at exactly that, peak capacity of common columns in size exclusion. And basically, here's a rule of thumb number 13. You're going to get basically 13 baseline resolved peaks. So if you take, remember these are these nice linear resolving ranges based on that graph we drew a few minutes ago. So if you take this range, for example, for Cephedex G10, and you break that into 13 equal parts, will your two analytes that you're interested in land in two different regions of those parts, right? And if they do, you can have some confidence that your species are going to resolve by size exclusion if you're using this material and you're following best practices of the methods designed for this material. So take-home message, we're not talking about super high resolution here. We're talking about pretty poor peak capacities divided across what can be, let's take a look here, what can be some really, really broad molecular weight ranges. So we're not talking about resolving, 100 kilodaltons from 100.1 kilodaltons, right? We're not talking about a 100 Dalton resolution at the 100 kilodalton level. These are generally methods for separating very large protein complexes or very large polymer products from very small protein complexes or very small polymer products.
Okay, so just a few more practical considerations that we're going to need to be able to dive into the literature on size exclusion chromatography. The first is that, okay, so we call it size exclusion chromatography, SEC. But actually there are other really common names for this. So it's often called gel permeation chromatography. That's GPC. or gel filtration chromatography, GFC. The thing to know is that these are all the same thing. It's the same separation mechanism. Um, the concept gel here comes from those materials we were just talking about, Sephiros, which is cross-linked agarose, and other materials that originate as hydrogel materials from mostly from the biochemistry community and protein separations. And so we basically look at a mechanism where particles are made of gel and how deeply do these analytes permeate into those gel particles. It's the exact same thing. So I mentioned biology as kind of the origin of some of these materials. It's also one of the key application areas for this, right? Uh, so applications of SEC. First of all, in biology, one of the things people like here is to look at what we call quaternary structure or fourth degree structure, quaternary structure, which implies, just not to give a huge biochemistry lecture here, but the primary structure is essentially the sequence of amino acids. Secondary structure is kind of a two-dimensional folding of that sequence. The tertiary, the third degree structure, is sort of the 3D structure of this thing. So quaternary structure implies the macro structure that proteins make with each other. So when multiple proteins come together to form complexes, and you can imagine two large proteins coming together to form a complex, it's going to be a very large structure. And so it can be very useful to have size-based separations to study and isolate these things. So that is one of the big application areas, and other just kind of general protein purification. Um, and then it is highly used in polymer synthesis or characterization, polymer characterization, as both size-based purification but also as a means for studying polydispersity, which is something that you can get from dynamic light scattering. I know a lot of the groups in our department use DLS for this purpose, but you should know that size exclusion chromatography and studying the shapes of the peaks essentially as they come out of this resolving range gives us some information about the polydispersity. If you are not a polymer scientist and you don't understand polydispersity, that's okay. We're not going to learn it here. But understand that this is another major application for size exclusion chromatography. I guess the last thing I'll tell you is that SEC is used both as a prep technique, and so that means that in the kind of the large volume, things like flash chromatography, which we've talked about previously in the semester, formats, you can get size exclusion or gel permeation or gel filtration columns, and also as an analysis tool. And we can actually see some evidence of this in these applications that we just looked at, right? If you're looking to do a size-based purification, this is likely a prep application. If you're looking to purify proteins, you're likely doing some prep work. If you're looking to study the polydispersity of your synthesized, polymer mixture, or to understand factors of binding, right, of quaternary structure in protein complexes, that's likely an analysis-based application. So I think this is going to close out what we're going to say about size exclusion chromatography, and the next thing we are going to move on to is chiral separation.